Alright, so we are not using the video system, the beta projector, so I think it should be okay to just go like this. It is recording now, so I can now track it by moving it like this. Excellent. Okay, so what I want to do today, after you get a little bit dizzy watching that, is talk a little bit about some things we'll be seeing later. I don't want to go into too much detail on them right now, just give you a little bit of sense of what's out there. And then it is almost a requirement that you have to start problem-solving classes with induction. Right? Has everybody here done proofs by induction? Right. Is anybody here brave and possessing an identification on them, like a driver's license? Okay. Would you mind taking that out?
No problem. Here you go.
All right. Does everybody know that your name is Catherine?
I hope so, maybe? I don't know.
No, everybody knows that your name is Catherine. Everybody is named Catherine.
Oh.
Everybody in the world is named Catherine. This is known as the Catherine theorem, which we will prove later today using induction. All right, but I want to start first with the following. So consider A plus B times B plus C times C plus A greater than or equal to 8A, B, C. And let's assume A, B, and C are greater than 0. So this is a claimed inequality. There are an enormous number of inequalities you can prove in life, and we'll prove many of them. What I want to do right now is start with something that you are not supposed to look at for today. I will be doing this often. And just, what are your first thoughts when you see something like this? Really open question. Yes?
To expand it?
So one possibility is to expand. I think that's not going to be useful here because you're going to end up getting a lot of cross terms, but it's not a bad thing to consider. In fact, really, it should be expand/simplify. Is that I might actually give you something that's already expanded, and can I do some algebra and regroup it? I consider Henry David Thoreau the patron saint of mathematics. How many of you have ever read his Walden? Read it, jogged around it. So what is his great advice? Anybody remember? Simplify, simplify. You get back to the basics. When you have something involved, it is often worthwhile to simplify it. When you're doing the long calculus or algebra problem, spend a few minutes seeing if you can rearrange it into a better way. Now, of course, you could simplify, simplify, simplify to simplify, but the extra simplify is, I think, for emphasis, it's okay to have. So one possibility is to expand. What else might you think of when you do something like that?
I feel like I'm interested to know if it actually works for some certain values.
Yes, test it. There's something which is known as typos, where people often will write down formulas incorrectly. There are books of tables of integrals where there are mistakes. Try a few values. Try to get a sense. Do you think this inequality is tight? When you see something like this, what jumps out at you when you look at it? Anything in particular? Yeah.
Well, if A, B, and C are all equal.
Good. So try A equals B equals C. And in a special case like that, you will see that it's going to be an equality. Yields true. In fact, it's true with an equal sign. So maybe, in fact, A equals B equals C, maybe that's the minimum value for the left-hand side relative to the right-hand side. That could be an important value. Also, when you take A equals B equals C, it gives you some idea of why there is an 8 here. Whenever you see problems, if you're doing a math competition, you see 2018, okay, this was probably an exam question written in 2018. Frequently, these numbers don't matter. How much does 8 matter? Any idea how we should write 8? Yeah, maybe 8 is 2 cubed. Okay, sorry. 8 is definitely 2 cubed. But maybe the fact that 8 is 2 cubed is useful for this problem. Maybe we could generalize, or maybe we could downgrade. Could you think of maybe an easier case to look at? So could you think of any way to generalize or maybe a simpler version of the problem?
Generalize to n cubed and then set n equals 1.
We could generalize to
N cubed and then for n cubed ABC and set a 8.
Okay, but then what would so is 8 with n cubed?
Yeah, then.
Okay, but I mean that's not battling on the constant. Right? So I'm going to assume that that's really the right constant because I wrote it down. But this is the constant with 3. Why do you think 3 is playing a role here? Yes. There's 3 terms. So again, you really want to get into the habit of how do you take something like this and look at it. So what might you guess would be another inequality that's true? Yes.
A plus B
Yes.
is greater than or equal to 2AB. That's fine.
Okay. So we have some. But now let's also look at dimensional analysis. I always like to use units. What units would this side have? Say meters cubed. This would be a volume. And this would also be a volume. So I would have two things of similar units. So I don't think A plus B would be the right way to go. I'm sorry?
No.
Well, you're on the right track.
Maybe AB squared.
Yeah, but I might want to write that as maybe A plus A
That's what
is greater than or equal to 2 squared AB. So that could be a good thing to try. Or maybe A1 plus A2, A2 plus A3, all the way down to AN plus A1, greater than or equal to maybe 2 to the n, A1 through AN. So again, we're not trying to solve the problem right now, we're just trying to see how would you attack something new like this. Do you know the most important logarithm in mathematics, the W log, without loss of generality? Alright, so without loss of generality, this is an extremely useful expression. It basically means I'm too lazy to write the details of all the cases because they follow very similarly. I'm going to just do one case, and this case is enough to really understand what's going on. Do you think we need A, B, and C to be greater than 0? Do you think that this could be true if we had, say, negative numbers as well?
maybe for like even terms, numbers of terms.
Could be. So you think that there could be, if there's an odd number of terms, that maybe we could make one of the factors negative. Or we could even maybe make one of the factors 0. If B equals negative A, we could get this factor to be 0, and then the whole product is 0. And then as long as we have enough negatives. So you always want to check and see how important are those conditions. Because A, B, and C are all greater than 0, and both sides have the same dimension, we can rescale. So we'll call it dimensional scaling. You can assume something about A, B, and C. There's lots of different ways you could do this. Without loss of generality, what could you assume about A? Yes?
A is greater than B and C.
So one possibility is you could do an ordering, and you could say, it's enough to consider maybe A greater than or equal to B greater than or equal to C. That's absolutely one thing you can do. What else, if you wanted to, could you assume about the value of A? I claim it's enough to study this just one value of A. What value can you study it for? 1. Or any value you want. I can divide through by A. And then I would get 1 plus B over A, B over A plus C over A, C over A plus 1 is greater than or equal to 8, B over A, C over A. I can divide through by A. I could set A equals 1. Yes?
Wouldn't it just be 8BC?
Yeah, it would just be 8BC. No, because I have to divide this side by A cubed.
Oh,
Right? And this is, I can only do this because of the fact that both sides have the same dimensions, both sides are volumes. So I could choose A to be 1. But maybe it's better not to have A be 1. Maybe it's better to have a different quantity be 1. Any thoughts on what other quantity you could choose to be 1 without loss of generality?
I mean, isn't it just any other?
So you could choose A, B, or C to be 1, yes. So that'll be essentially the same as A equals 1. Yes?
ABC.
Yeah, you could take A, B, C to be 1. Right? Because I can rescale by whatever that product is. And now I would have 3 numbers whose product is 1. The other one I could also do is I could do A plus B plus C equals 1. You might begin to see, oh, maybe this reminds me of that stuff I forgot from Calc 3, Lagrange multipliers, where I have a constraint. Oh, this allows me to reduce the number of variables by 1. So we will spend a lot of time attacking problems like this. I wanted to just do a little bit right now and just give you a sense of thought processes of how do you take something new, how do you break it up into cases. Sometimes it's easy to generalize or look at simpler cases and say, A plus B, B plus A, and get a sense of where these numbers are coming from. Sometimes it's good to try to look for extreme cases to get a sense of where these constants are coming from. And there's often a lot of information in the constants. Is it a binomial? Is it a pure power? Is it a factorial? You try to get a sense of where these come from. And then these ideas here, we can basically remove a variable. That's wonderful. And that makes the calculation a lot easier. Okay. So this is basically all I wanted to say about this. So everyone has seen induction before. There is nobody who has never seen induction. Excellent. So I'm not going to then go through and do the standard, baby examples. I will go straight to the Kaplan theorem. So proofs by induction. So you start off with some statement Pn, and here it will be in any group of n people, all are named Kaplan. And will you accept as a friendly amendment that some might incorrectly spell Kaplan with a C?
I guess.
Okay, I'll go because we can prove the strong Kaplan theorem.
Oh. I want the strong.
The strong,
Kaplan.
okay.
Yeah.
So it will be spelled okay. Alright? Step 1 is the base case. Is P1 true? If I have a group with just one person, well, is everybody named Catherine? Well, I don't know. That seems a little bit hard. So let me make my thing a little bit easier right now to help me. In any group of n people, all are named the same. So everyone has the same name. So I'm not going to initially prove that everybody's named Catherine. I'm going to make it a little bit easier for myself. I'll prove that everybody in the world has the same name. And since I know the name of at least one person in the world, which is Catherine, I will now know that everybody is named Catherine. This is a great way to attack a lot of problems. Prove something a little bit easier first, and then go from there and get a corollary. Does everybody agree that the basis case is trivial? That if you have a group with just one person, clearly everybody in that group has the same name. So now inductive step. So we get to assume Pn is true, prove Pn is true. Okay? So what do we get to assume? We assume whenever we have a group of n people, they all have the same name. So let's consider a group of n plus 1 people. I apologize for the drawing. This guy here. And this person will be John Travolta doing his goodness. All right. 1, 2, 3, n plus 1. By inductive assumption, what do I know about these n people? I'm sorry, raise your hand. Who? Yes, Catherine? Same name, thank you. I technically do not know your name is Catherine yet. I'm just acting on a hunch. What do we know about these last N people? Yes, Catherine again. Same name. Ah, but look, they got all these people in common. These are all in common. So because they all have the same name in those groups, and because there's a person in common, those names must be the same. So therefore, all same name. What's wrong? Yes?
Will you assume large N?
I am assuming large N. So what is explicitly the mistake?
So if you have P2.
Yes. So if N equals 1, I would have this situation and there would be nobody in common. So this is amazingly almost true. If we knew in every group of 2 people everybody had the same name, then yes, we would have in every group of N people everybody has the same name. Because you could just take your one special person and just pair them off with everybody. This is one of the most common mistakes people make. And when this is not recording, I will talk about a paper I have had to manage for the Journal of Number Theory, where people are claiming to have proven one of the biggest conjectures in mathematics, and they did a mistake like this. And it's like 20 emails later still trying to convince them that they have done the induction incorrectly. And so the problem is, when you write things down, there is a tendency to assume that you've written down something generic, but you must be careful. We only know this is true when N equals 1. When we write something like this, as soon as we talk about those people there, it's implicitly assuming N is large. Okay? Any questions about the Catherine theorem? Alright. Now, did I prove that everybody in the world is not named Catherine? No. This is just not a valid proof that everybody is. It's possible that everybody in the world is still named Catherine. Right? Unlikely, but it is possible. Let's see. As a fun exercise, modify proof to show every integer is a perfect square. Now, this is clearly a false statement, right? So the question is, can you modify the proof I just gave you to prove this false statement that every integer is a perfect square? Obviously, you're going to have to bullshit, right? You're going to have to do something wrong. Okay? But can you modify that proof to give another false proof? The other way this theorem is often, it's not usually done as the Catherine theorem, it's normally done as the horse of a different color theorem, to prove that all horses are the same color. And then what's nice is later on, when you're doing your arguments, if you want to disprove something exists, you would say, well, that would be a horse of a different color, which doesn't exist by the previous lemma. Right? So it's really good to go through stuff like this to get a sense of where things break down. Right? Since it is required, we will do Pn is 1 plus 2 plus n is n plus 1 over 2. We always have to do arguments like this. Okay, has everybody seen this before? And have you seen the Gauss proof of this? So the story is when Gauss was very young, he was in school, the teacher was having one of those days and wanted to shut the little brats up and told them, add up the numbers from 1 to 100, expecting to get a few minutes of reprieve. And Gauss immediately blots out the answer. So the way to do this quickly is let Sn be the sum. Well, if I write the numbers backwards, it's the same sum. So I get twice my sum. Each one of these is going to be n plus 1, and I have it n times. So you get Sn is 1/2 n plus 1. So this is the brute force approach. It's very nice, it's very elegant, but it doesn't generalize well. So because it doesn't generalize well, we will instead do the proof by induction. But it's worth seeing something like this. You might have seen something similar to this when you proved the geometric series formula. Does everybody remember the proof of the geometric series formula? If not, please speak up.
I do not remember.
Okay, let's do the proof of the geometric series formula because it is worth knowing. It's similar to what we've just done here. All right. I was saying this with the camera recording. My first year at Williams, I was teaching differential equations in the spring, and linear algebra is not a prereq for the class. I can't teach differential equations without doing systems of linear equations. It's just wrong. You lose the ability to model a lot of things. So I was going to deal with 2x2 matrices. So I asked the class, does anybody want a review of 2x2 matrices, or is everybody comfortable? You're complete silence. Everybody's fine. Nobody want, okay. We had clickers. And so I asked people, you press 1 if you want a review, press 2 if you don't. I'm not going to report on the results to the class. I'm just curious. 43% wanted a review of 2x2 matrices, and were not willing to speak up. So almost surely, if there's something you want to see, odds are there is somebody else who wants to see this also. Please speak up. So a geometric series, one of the most important in mathematics. So let's say Sn is 1 plus r squared plus r to the n. Then we can do something very similar to what Gauss did. We'll multiply by r, and that's going to shift everything over by 1. So 1 goes to r goes to r squared. All right. Instead of adding, what do you want to do now? Oh, sorry, r to the n plus 1. Thank you. So what would you like to do now instead of adding? Subtract. You're going to get massive cancellation. And so when you subtract, Sn minus rs, oh, that's just 1 minus r times Sn is 1 minus r to the n plus 1. Or Sn is 1 over 1 minus r minus r to the n plus 1 over 1 minus r. Most people will write this as just a numerator divided by a denominator. They're not going to split it up like this. I like splitting it up like this because it now shows you as n goes to infinity, this is what you expect the main term to become. And as long as the absolute value of r is less than 1, this will go to 0. So this goes to 0 if the absolute value of r is less than 1. And that will give you that the infinite sum is just 1 over 1 minus r. This actually gives you how far away you are. Wonderful, wonderful result. Okay? This is one of our go-to sequences. But it's the same idea as what Gauss did, is you want to combine things in a clever way. Sadly, you cannot always combine things in a clever way, but when possible, it's worth knowing. All right. Any questions on the geometric series formula? As an aside, how many of you have taken real analysis? Okay. One of the hardest things to do in a math class is to interchange orders of operations. When can I interchange a sum and a sum, or a sum and an integral, or two integrals, or a derivative and a sum? If you're a physicist or an economist, it doesn't really matter, you just interchange. But if you're a mathematician, you want to justify. And so if I have a series, maybe I have an infinite sum, when can I differentiate term by term? So I realize this is a little bit of a digression, but this is one of the fun things. From calculus, what's the derivative of a sum? Sum of the derivatives. Did you prove this? Hopefully you guys proved the derivative of a sum is the sum of the derivatives by looking at the limit. But you only prove this for two terms. Derivative of a sum is the sum of the derivatives. So let's say I know we still have this in the bank. Let's say we know this is true for two sums. So now if we have f plus g plus h, and we want the derivative of that, we can write that as f plus g plus h. And now we have the derivative of the sum of two things. That's now the derivative of f plus g plus the derivative of h. This is now f prime plus g prime plus h prime. We go through a large amount of chalk, and we get f prime plus g prime plus h prime. So if you know the derivative of a sum of two terms is the sum of the two derivatives, then you get it for three, and by induction you can do it for any finite. And that's the point that's often missed, is that the result only works for finite sums. If you have an infinite series and you want to differentiate term by term, great, but you have to justify it. The fact that the geometric series has such rapid decay allows you to justify that. The other thing which is really nice is the tail of a geometric series is itself a geometric series. And that allows you to replace it with a nice finite sum with a beautiful error term. So for geometric series, you can justify a lot of things. Almost surely you never proved this in your Calc 1 class. They basically, if you were lucky, did the derivative of a sum of two functions is the sum of two derivatives, and then you just kept using the derivative rule when you had more and more functions. But technically there was an induction that should have gone on. All right, let's go back to the standard proof. And this will lead to an extra credit assignment, which, if you can solve to my satisfaction, will lead to an extremely high grade for the class. It's something that I've had on my mind for years that I would love to see a proof of. And if you can make this work, I am happy to talk about giving you an A for the course. And yes, I realize this is day 2. All right, so here's the proof by induction. Is P1 true? Yes. 1 is equal to 1 times 2 over 2. We've all seen this. Everyone has seen this proof. I can go fast. All right. So now assume Pn. Show Pn plus 1. Well, let's study 1 plus 2 plus n plus 1. Well, because we are assuming Pn is true, we are assuming we know something about this. So it screams substitute. So by the inductive assumption, this is n plus 1 over 2 plus, I'm going to write this as 2n plus 1 over 2, so I have a common denominator. This is then going to be n plus 1, n plus 2 over 2, and if you love being exceptionally pedantic, you can write it as n plus 1 times n plus 1 plus 1 over 2. So it is exactly of the form there. If you feel that this is overkill, it's perfectly fine to stop here. Okay? This is a proof of the sum of the first powers of integers. What made this trivial is that I told you what it's supposed to equal. And because I told you what it was supposed to equal, you can just substitute in here and then do simple algebra. Right? One of the advantages of being at the board is I can do a very fast search and replace. Right? Let's look at sums of squares. Now it's n plus 1, 2n plus 1 over 6. First step is still true. And now, the algebra changes just a little bit. And so now I'll have n plus 1, 2n plus 1 over 6 plus n plus 1, and then how do we want to write what's left over? It's n plus 1 squared, so maybe 6n plus 1 over 6. Because now I can pull out an n plus 1 over 6, and I'll have 2n squared plus n plus 6n is going to be plus 7n plus 6. Just doing the algebra? Yes? Haven't made a mistake yet? And so this will then become n plus 1. Now 2n plus 7, n plus 6, I'm going to get an n plus and a 2n plus. And so I'll want a 3 here and a 1 here. Is that right? I'm sorry? Oh, no, sorry. I need
3 over there.
Right, I need a 3 over here and a 2 over here. Now it's right. And notice, look, n plus 1, n plus 1 plus 1, 2, n plus 1 plus 1. So when you do the algebra, it comes out correctly. So a little bit more algebra, but essentially the same thing. If I gave you sums of cubes and I told you what it was supposed to equal, would it be hard? No, it would just be do some algebraic simplifications. If you go to Mathematica or go to Wolfram Alpha Online and just plug it in, it will simplify for you. Now, where things get interesting is if I ask you to do it for any k. Do the kth power and get a formula in terms of k. There are formulas for that. The hard part is knowing what the answer is. What do you notice about the answers so far? We only have 2 data points, but yes?
The largest power is 1 greater than...
Largest power is 1 greater. So largest power is 1 greater. Okay, good. What else? So the largest power is 1 greater. It hasn't been said explicitly, but it's a polynomial. Any thoughts on the coefficient of the largest power? So the first it was 1/2, then 1/6.
It's 1 over the factorial of the largest power.
Good, let's say 1 over the degree factorial. And if you think about this, I could approximate this with calculus. This is looking like the integral from 1 to n of x squared, which should get me x cubed over 3. Oh, so wait a minute. That's x cubed over 3. That's not x cubed over 6. Or maybe it's not the factorial. The iPad just nodded. I've never seen that before. The iPad agrees with me. So, okay, so if we looked at the sum of the squares, if we do calculus, that should be the integral of x squared, which is x cubed over 3.
But the largest term has a 2.
The largest term here has a 2. So we have n times 2n over 6. So you could put the exclamation point here for emphasis, and that would be okay. So it seems like the largest term might be 1 over degree coming from calculus. The last one is the constant term is 0. Well, if you think about it, if I start at 0, I'm going to have a sum of 0. So if you don't know what the formula is, one of the things you can do is you can actually try to do small cases. I can do a couple of values by brute force. And then if you know the first couple of things, now you can say, I think it's going to be a polynomial. Let's say I want to do 4th powers. So if I do 4th powers, it'll be a polynomial of degree 5. But I believe that the constant term is 0, and I believe the largest term is going to be 1 over 5. And so maybe if I just evaluate 4 values of n, I can then say there's only going to be 1 quintic that goes through those points. And then once I have that quintic, then I can try to prove that it works. So you could do some data analysis and gather some data to figure out what the polynomial should be. Okay, I'm going to move it back to how it was before because it seems to not like the clicker 10 micrometers to the left. All right, but so is everybody clear on how you would try to gather data and then do some method to find what is the only polynomial of degree 5 that fits through this? I want to show you another way to attack these problems. So I'm going to assume we know this statement. So one of the big questions in mathematics is always, how deep is a result? Or how much do you need to know to prove something? And so my question is, imagine you do a lot of work and you find a formula for the sum of the first and the second powers. Can you deduce everything from that in a nice way? How many of you are familiar with L'Hopital's rule? There's a way to use geometric series and L'Hopital's rule to actually get formulas for sums of powers. Once you get to beyond sums of squares, the formula is so painful, it's not worth doing. But you could do it if you were looking to waste many, many minutes of time on algebra that nobody else wants to see. It's not a good approach, but it's an approach that would work. It's entirely formulaic, and it does not require you to know what the answer is. So here's an interesting idea. So let's consider the sum k goes from 1 to n of k squared. What does this equal?
N squared plus 1 squared.
Yeah, n squared, n plus 1 squared over 4. I'm going to expand this out. This is going to be the same as the sum k goes from 1 to n of k squared plus the sum I goes from 2 to n of I, and then the sum j goes from 1 to I minus 1 of j, and I put a factor of 2 here. So when I expand things out, I will have two types of terms. I'll have terms when you multiply by yourself, so I'll have the 1 squared, the 2 squared, the 3 squared, the 4 squared. That's covered here. Then I'll also have the 1 times 2, the 1 times 3, the 1 times 4, as well as the 4 times 3, the 4 times 2, the 4 times 1. I want to make sure I don't double count everything, so in the ij, when I have two different terms, I'll let j be the smaller one. It goes up to 1 less than I, and then I will have to go from 2 all the way up to n. So this is just an expansion, okay? So now let's analyze it a little bit. So I've got the sum. I'll use a different letter here. I'll use m. Let's keep using as many different letters as possible. So I'll have the sum m goes from 1 to n of m squared plus twice the sum I goes from 2 to n of I. Now what is the sum j goes from 1 to I minus 1 of j? What does that equal? Yes.
It's the n, that's n plus 1 over 2.
Good, and what do I take for n?
I minus 1.
So I take I minus 1, so good. I minus 1 times I over 2. And now here's where the miracle occurs. This is the sum, n goes from 1 to n of m squared, plus the 2's cancel. I'll have a sum, I goes from 2 to n. I have I cubed minus I squared. I cubed minus the sum, I goes from 2 to n of I squared. But I want to do something first. In this sum, could I have the sum start at 1? Would it change anything? Because I have the fact of I minus 1. So I could lower the sum to start at 1. I could even lower it to start at 0 if I wanted. So I'm going to lower the sum to start at 1. Okay. 1 and 1. Excellent. And now what miracle do you notice? Yes?
The outer term getting canceled.
Yeah, this term cancels with this. I and m are just dummy variables. The sums of the squares completely cancel. And I'm left with the sum of the cubes. So you end up getting the sum, I goes from 1 to n, of I cubed is n squared, n plus 1 squared over 4. We actually get the sum of the cubes just by knowing the sum of the first powers. Amazingly, we completely bypass the sum of the squares. So my question is, if you assume that you know the sum of the first powers and the sum of the second powers, can you do a trick like this to get everything? Or if not, what do you need to assume to get everything? Is there a finite set of power sums that you need to know from which you can always play a game like this? So if you can push this far, this could be a paper that could be published. I am an editor at several journals which would like a nice elementary result like this. And to me, I think it's fascinating how you have this beautiful, perfect alignment and cancellation. Yes?
So this is the proof that would get us an A.
If not an A, it would get you damn close to an A. I mean, you'd be within striking range.
And so why hasn't anybody done this yet then?
I mean, a lot of times it's a question of who noticed these things and who pushes it. It is possible that this is in the literature. I frequently save things and leave them for students to think about. So I've thought just a little bit about this, and I've done some calculations for very small values of powers, but not anything far enough to have any real sense of what will happen. And can you always break things down to these constituent building blocks? But to me, I find it interesting that you can do something like this. And there are some elementary proofs where they try to solve these power sums geometrically. All right, so I will end with, we'll skip the cookie problem for now. I'll quickly do a tiling problem, and then I will mention the tie. I don't know if anybody's able to understand the tie. Beautiful tie. Yes? I do not wear this tie to services today. It would not be appropriate. I have worn this tie to meetings with high-level college administrators. So much of math is the right perspective. I will show you another example of this with Rubik's Cubes later. Actually, anybody know what this is?
Like in terms of functionality?
Yes. What is it called? A tie clip. Yeah, it's actually a working slide rule tie clip. I got it from an engineer cousin in my family. The last time I showed this at Williams, students both didn't know what a tie clip was and what a slide rule was.
I have a friend who did all of his chemistry exams with a slide ruler because he thought he was so cool.
Well, if people do need to borrow slide rulers, I have a bunch of them, and so we do have slide rulers. And then if you've never seen it,
He still finished in 4 hours.
the circular slide rule is even better. But I don't know if you were able to read it from this.
Oh.
If you put this about halfway.
I don't know what the second one is.
Yeah.
All right,
I know.
I'll leave it for later. I'll leave it for later. But it's the power of writing things properly. And a lot of times in math, the answer will be in front of you, but you may not realize it. So you have to find the right perspective to adopt. So let's consider we have 1x2 tiles. We want to tile without overlap a 2x(n) board. And the question is, how many ways are there to do it? So you want to start off by gathering some data. When n equals 1, how many ways are there to tile? One way. When n equals 2, how many ways are there to tile? So how many ways are there to tile when n equals 2? 2 ways. We can go like this, we can go like this. There's 2 ways. When n equals 3, how many ways are there? I could go up like this, in which case that I could go either up, up, or right, right. Or I could start off by going right, so this one has to be right. So how many ways are there? 3. So you can go to the online encyclopedia of integer sequences, you can put in numbers 1, 2, 3. It's not quite far enough to really be comfortable. If we start to do 4 or 5, then we start to get some more information. And in the interest of time, I will tell you when n equals 4. Anybody want to guess how many ways? It's natural to guess that, so.
I would guess. Oh no, it's not 4.
It's not 4.
Yeah, it's not.
I think it's 5.
It's 5. And what do you think it is when n equals 5? I know you know iPad, but you have to let the students answer. I'll say something all right. It's 8 ways. Anybody detecting a pattern now? 1, 2, 3, 5, 8. 13. It's proof by induction. Let Sn be the number of ways with n. And now, when you look at what's going on, you either have to start off with an up arrow like this, or 2 right arrows. So if you start off with an up arrow, you now have an n minus 1 by 2 board. How many ways are there to do an n minus 1 by 2 board?
Number of the previous.
Yeah, it'll be Sn minus 1 ways. And if I have 2 right arrows, how many ways are there? Sn minus 2. And so you get Sn equals Sn minus 1 plus Sn minus 2. It's the Fibonacci relation. All you need to do now is get the initial conditions. And the initial conditions are S1 equals 1, S2 equals 2. And you'll get the Fibonacci numbers.
And what other aspects of, like, because I heard it comes, that sequence is like everywhere.
The sequence is everywhere. I mean, we could do almost an entire semester on Fibonacci's. We will do a lot more with them later. I'm not quite sure why it wants to keep going. I will just end, we've got about 1 minute left, with a quick thought on the size of Fibonacci's. So let's look at your Fn plus 1 is Fn plus Fn minus 1. We get Fn plus 1 is greater than or equal to twice Fn minus 1, because the Fibonacci's are increasing. And we get Fn plus 1 is less than or equal to twice Fn. So from this you can get that essentially Fn is growing slower than 2 to the n. Because if I kept doubling, I would increase by a factor of 2 every time. And it's basically going faster than square root of 2 to the n. This may be a little bit long for small values of n, I don't care. We're running out of time. But it gives you some quick estimates of the growth rate of the Fibonacci's. The Fibonacci's grow exponentially fast, somewhere between root 2 and 2. And this is the power of getting some rough approximations to what's going on. All right, so a lot of good stuff for today. I will be saving a card trick probably for the next class. If people are worried that I have a rigged deck, you are welcome to bring a deck of your own. I can quickly I'm happy to use that deck too.